Welcome to AI Frontiers, where we explore the cutting edge of artificial intelligence research. Today, we're examining robotics breakthroughs from June 6, 2025, that are fundamentally challenging how we think about human-robot collaboration. We'll discover why forcing humans to act like robots actually makes robots worse at learning, explore agricultural systems achieving over 80% success rates in real orchards, and meet soft robots that combine precision with adaptability in ways previously thought impossible. Picture this scenario. A robot is watching you make a sandwich, learning not just what you do, but where you look while you're doing it. This sounds helpful and intuitive, right? However, here's the twist that's completely turning robotics research upside down. When researchers attempted to make humans demonstrate tasks using robot-like interfaces, thinking this would create better training data for the machines, the robots actually became significantly worse at learning. We're talking about dramatic performance drops, with success rates plummeting from nearly 70% down to under 20%. This counterintuitive discovery suggests that forcing humans to see and move like robots might actually be one of the worst possible approaches for teaching them effectively. Today's episode covers 19 breakthrough papers that are reshaping our understanding of robotics and human-machine interaction. We'll uncover how the fundamental tools we use to teach robots are deeply flawed, explore revolutionary soft robots that can bend like biological muscles while maintaining computational precision, and examine agricultural robots that have finally achieved the reliability needed to work alongside farmers in real commercial orchards and fields. These discoveries reveal that the future of robotics isn't simply about building better machines, but about understanding how humans and robots can truly collaborate as partners. Computer science robotics resembles conducting a symphony orchestra where every instrument represents a different kind of intelligence working in harmony. The mechanical violins consist of actuators and sensors providing physical interaction with the world. The algorithmic cellos encompass planning and control systems that coordinate complex behaviors. The artificial intelligence brass section handles learning and perception, processing vast amounts of sensory information. The human woodwinds manage interaction and collaboration, bringing intuition and expertise to the partnership. The true magic emerges not when each section performs perfectly in isolation, but when they harmonize together to create something far greater than the sum of their individual parts. Our first major theme involves a revolution in human-robot learning that challenges fundamental assumptions. Ishida and colleagues discovered that robot-like interfaces actually fail to capture the essence of human expertise. Their research revealed that natural human demonstration methods work approximately 3 times better than constrained robot emulation approaches. Using sophisticated eye tracking technology, they uncovered that humans employ sophisticated gaze strategies that are intimately connected to natural sensory motor capabilities. The counterintuitive finding suggests that making demonstration conditions less robot-like actually produces dramatically better robot learning outcomes, fundamentally challenging how we approach imitation learning systems. The second theme showcases a breakthrough in smart soft robotics that solves a classic engineering trade-off. Researchers successfully embedded shape memory alloy wires into pneumatically actuated soft robots, creating hybrid systems that achieve both precision and adaptability simultaneously. The results were remarkable. Angular positioning error dropped from 5 degrees down to just 2 degrees. While response time improved dramatically from 19 seconds to only 3 seconds. This represents a 6-fold improvement in speed while simultaneously enhancing precision. The breakthrough moves robotics from the medieval armor approach of rigid precision toward the athletic suit model of intelligent flexibility, combining safety and adaptability without sacrificing performance. Our third theme demonstrates robotics finally achieving commercial viability in real-world agricultural applications. A sophisticated dual-arm apple harvesting system achieved success rates exceeding 80% in actual commercial orchards, while reducing harvest time by 28% compared to single-arm operations. These aren't controlled laboratory demonstrations, but robots working in genuine agricultural environments with real farmers. Dealing with unpredictable weather conditions, varying fruit sizes, and all the inherent complexity of natural farming environments. Additionally, autonomous soil sampling and analysis systems can now process samples within 10 minutes while maintaining accuracy for pH and macronutrient measurements, representing a dramatic improvement over traditional laboratory methods, requiring days or weeks for results. 3 breakthrough stories emerge from this research that fundamentally challenge our assumptions about robotics. First, natural human interfaces outperform robot emulation approaches by an astounding 250%, revealing that constraining human capabilities actually degrades the quality of training data. Second, smart materials integration creates robots that are simultaneously precise and gentle, solving the classic rigid versus soft robotics trade-off that has limited applications for decades. Third, agricultural robots have finally achieved the commercial reliability needed for widespread deployment, with comprehensive field testing validating consistent performance across diverse real-world environments. These discoveries collectively suggest that integration and system-level thinking now trumps individual component optimization. Today's featured paper by Ishida and colleagues represents a systematic investigation of human demonstration interfaces that challenges everything the robotics community thought it understood about imitation learning. Their research employed sophisticated eye-tracking technology combined with careful performance measurement to reveal how different interface designs affect human cognitive processes. The study discovered that robot emulation consistently degrades human expertise, while natural gaze data improves robot task success rates by 3.6 times compared to constrained demonstration conditions. This work fundamentally challenges the assumption that training data should match deployment conditions as closely as possible, suggesting instead that we need sophisticated translation mechanisms between human expertise and robot capabilities. Consider this analogy. A master chef teaching an apprentice doesn't tie weights to their arms to simulate working with heavy tools, nor do they wear vision-limiting goggles to match poor lighting conditions. Instead, they demonstrate their craft under optimal conditions, allowing their expertise to shine through completely. The apprentice then learns to adapt these demonstrations to their own capabilities and environmental constraints. Ishida's research suggests that robot learning should follow this same principle. Human expertise involves unconscious gaze strategies and natural sensory motor coupling that artificial constraints fundamentally disrupt. Rather than constraining humans to match robot limitations, we need sophisticated translation systems that preserve the richness of human demonstration while making it accessible to robotic systems. The implications of this research point toward an entirely new paradigm in robotics development. Instead of making humans more robot-like through constrained interfaces, we should focus on making robots better at learning from naturally expressed human capabilities. This requires developing sophisticated translation mechanisms that can convert the full spectrum of human expertise into robot-appropriate actions and behaviors. The approach suggests we should amplify rather than constrain human expertise, leveraging natural capabilities instead of artificially limiting them. This paradigm shift could accelerate progress in teleoperation, collaborative robotics, and imitation learning by treating human intelligence as a resource to be enhanced rather than constrained. Sometimes the most significant breakthroughs come from counterintuitive approaches that challenge our fundamental assumptions. Looking toward the future, robotics appears to be evolving much like musical instruments throughout history. We didn't create better music by forcing musicians to play with mechanical precision, but by developing instruments that responded more sensitively to human expression and creativity. Similarly, the future of robotics lies in creating machines that function as sensitive instruments, responding to the full spectrum of human intelligence and expertise. Agricultural systems will amplify farmer knowledge and decision-making capabilities. Soft robots will enable gentle precision in healthcare and human assistance applications. The boundaries between human and machine intelligence will become increasingly fluid, creating partnerships that unlock capabilities impossible for either humans or robots to achieve independently. The research we've explored today represents far more than just technical advances in individual components or algorithms. It reveals a field undergoing fundamental transformation, from a discipline focused on building better machines to one centered on creating more effective partnerships between humans and machines. This shift in perspective promises to unlock new possibilities that neither humans nor robots could achieve working in isolation. The key insight is that the most profound advances often emerge not from building more powerful individual systems, but from developing deeper understanding of how different types of intelligence can work together synergistically. Human-robot partnerships have the potential to exceed the capabilities of either partner working alone, creating new forms of collaborative intelligence. This research synthesis was created using advanced AI systems to analyze and synthesize findings from multiple robotics papers. The content was processed using GPT Anthropic Claude Sonnet 4 2025014 for comprehensive analysis and synthesis. Text-to-speech synthesis is powered by OpenAI's advanced audio generation systems. Image generation utilizes Grok's visual AI capabilities. All synthesized content has undergone human expert review to ensure technical accuracy and appropriate interpretation of the research findings. While every effort has been made to accurately represent the original research, potential oversights are acknowledged and all original paper references are provided for readers who wish to examine the primary sources directly. Thank you for joining us on AI Frontiers as we explored these groundbreaking robotics discoveries. Subscribe to continue receiving cutting-edge AI research insights delivered in accessible formats. Share your thoughts about human-robot collaboration and these surprising findings on social media. We encourage you to dive deeper into the original papers, which are freely available and contain additional insights that could inspire your own ideas about the future of intelligent systems. Connect with us across social platforms to join ongoing discussions about these developments. Keep questioning fundamental assumptions about AI's future, as the most exciting discoveries often emerge from challenging what we think we know. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by Archive Preprint Server.